Hey everyone. All right, this one should be fairly quick. It's more accumulation topics, but today we're going to talk about something that we've touched on in the past, but now we have a really cool tool to do it very quickly. So it's a first semester topic, kind of, but we're combining accumulation with something called total distance traveled. So if you remember back to first semester, if you have a negative velocity, you're going left, and if you have a positive velocity, you're going right. So if I took 3 steps to the left and then 10 steps to the right, I ended up at position 7, but I took 13 steps. That's the difference between total distance and displacement. Displacement is where you ended up relative to where you started, which we'll talk about again in a second. Total distance is how many actual steps you took to get there. So I will show you what I'm talking about by showing you an example of using this total distance versus displacement in an accumulation type problem. So I am giving you a velocity function. Remember, all of this applies to derivatives too, but we'll keep it in terms of motion for now. And I can ask you a couple questions. Well, before we do that, if you notice, I've given you the graph right here of this velocity curve. Remember, this is a velocity graph. That means this particle had negative velocity. It's below the x-axis from 0 to 2. And then it had positive velocity from 2 and on. So it went left for 2 seconds, and then I went right for 2 seconds. So some things I could have you find. I could have you find P of 2, for example. And to do that, don't forget, it is initial condition plus accumulation. If I ever want you to find a position, like, hey, I want to know where you're at time 2, well, I have to tell you something about where I started. Have to. Anytime I ask you about a position, you have to tell me where you started. So you would use P of 0, which I've given you, plus the accumulation component, where you started at time 0 to where you are trying to get time 2. Accumulate under your velocity curve. And P of 0 is 3, plus the cool thing about Desmos, once you start storing these values, you can manipulate them very quickly. So I will do 3 plus the accumulation from 0 to 2 of my velocity curve, which I already had stored in there, dt. So my position was 3 plus this value. If I want to know what this value is without the 3, I guess I could do this. Negative 5.333. 3 decimal places is fine. And that gives me a value of negative 2.33. That should make some sense. I traveled left, right? My velocity was negative. I'm traveling left during this time period from 0 to 2. Okay? So this key piece right here was your displacement. That's how far you actually ended up relative to where you ended up. So if I wanted to know the displacement from last time, the displacement is just the accumulation from where you're starting to where you're ending, 0 to 2 of your velocity. And then we just add that to the initial condition, and that gives us our ending position. Okay, so let's say I wanted to find my position at time 5, though. Not 5, let's do 4, a little bit smaller. Well, this particle went backwards, stopped at time 2, and then went forwards for a while. If I want to know my position at time 4, I could either use P of 2, which I just found, or you could go back to 0 again. And as long as you have that, the calculation will work itself out, even if the particle changes directions. So 0 to 4, v of t dt. So we plug it all in. It will be 3 plus, this time we'll change it a little bit. And this time we'll go to 4, 5.33, which is 8.33. And the displacement during this time period was just what happened from 0 to 4, v of t dt, which was this value right here. Interesting that it was the same backwards and forwards. Huh. Interesting. I'll have to look at that. Make sure everything's correct here. All right, so check it out. What is this saying? It's saying that this particle went backwards 5.33 from 0 to 2, stopped, and then went forwards 5.33, but from 0 to 4. Okay, that's what I'm, back it up a little bit. I'm confusing myself. From 0 to 4 is the displacement of how I ended up. So it didn't move forward 5.33. It went backwards, then forwards more. It just happened that these numbers were super similar. It happened where we ended up 5.33 units forward from where we started, even though we went backwards and then a lot more forwards. So it's almost like from time 2 to time 4, we traveled about 10 instead. Interesting coincidence in this problem. But again, the displacement in this case, the first 2 seconds, I ended up 5.33 units back. At the end of this, I ended up 5.33 units forward from where I started for this position. Okay. I guess really the thing I want you to take away from here is the positions. P of 2 was this value. P of 4 was this value. So started at 3, went backwards, and then went way forwards, faster. Okay. So now we're going to talk about something else, and this will help clear up a lot of what we just found, because this is why we need this calculation. There is something called total distance traveled. And to do that, I want to figure out how many total steps I took. So if we were to try to rationalize our way through this, we would think, okay, well, how far did I go backwards? So you could do this in 2 parts. You could think about what happened from t equals 0 to t equals 2. You could talk about how far I went during that time period. So from 0 to 2, v of t dt. What happened during that time period? Well, I took negative 5.333 steps backwards. So I traveled 5.33 steps. And then you could do the same thing, and this is what I thought I was doing last time, which is why I got confused. Talk about what's happening from t equals 2 to t equals 4. Saying, okay, now that I've stopped at time 2, what's happening in terms of how many steps am I taking from 2 to 4? And this one, we actually have to do this calculation. We haven't done it yet, but we can throw it into Desmos very quickly. And this will tell us the total the distance we walked forward in the positive direction. So from 2 to 4, that's that value I said earlier, about 10.667. So this particle took about 5 steps backwards from 0 to 2, and then it took 10 steps forward from 2 to 4. So if I asked you for total distance, which means the total amount of steps, one way to do it would be to add these 2 values, but instead of keeping the negative on the 5.33, make it positive. So 10.66 plus 5.333 for a total of 10.667 plus 5.333, which is 16. So in other words, I'm saying this particle only ended up at its position 4, 8.33 units, and it started at position 3, so it really only displaced itself by 5 units. That's this value we found here. But in actuality, it took a lot more distance traveled. It traveled 16 total steps, even though it only ended up to the right 5.33 steps. Okay, that's total distance. Now, This is a little tricky because you have to figure out, when I did it this way, you had to figure out where I stopped, and you had to do it as two kind of separate problems. Is there a better way to do this? Yes, there is. There's a much better calculation for finding total distance, and it works like this. If I want to find the total distance from 0 to 4, I can do it all in one move by doing one very simple thing. One very simple move. Going back to your graph, it added up this area. When I did this calculation right here, it added up negative area plus positive area, and it ended up with more positive area because I traveled forward more than I traveled backwards. I sure would love it if this area would be positive instead of negative. Is there any way to make it so a graph is always positive and never enters the negative realm? Yes, you can do something like this. Take it and take the absolute value of it. Now it flipped it, and it's going to find this as positive area, and this is positive area. It's going to take all the area and just make it positive. So that way it's accumulating only positive area, and look at the answer we get, 16, which is exactly what we found earlier by splitting it up. So I guess what I'm telling you, I give you the velocity curve, and I want total distance traveled from 0 to 4, you can actually do this in Desmos. Ready? Don't change the velocity curve. Change the calculation here instead. Put absolute value around your velocity, and that calculates total distance. It could change directions 50 times. It doesn't matter. The absolute values around it will cause the entire graph to be positive, and then you'll just be accumulating positive area. So to do this, absolute values around the velocity curve. And yeah, we get 16. Okay, that's the goal of today, is to know the difference between the three things I'm asking, which I keep asking you. To find position, you need an initial condition. To find displacement, I don't need an initial condition. All I need are where I'm getting displaced from and the time I started. And to find total distance, you also don't need initial condition. To find total distance, I just need to know the time you want me to find the total distance from. So if I wanted to know, hey, Mr. Particle, how far did you travel from time 0 to time 4? And here's your velocity curve. I just plug it straight into the calculation, and I get the total distance traveled. I do not need the initial condition in that case. All right, so let's do one more of these, but this time let's use a table and not an actual equation. So if I give you a velocity table, we'll make it fairly straightforward. T, V of T will go 1, 3, 2, 1, 3, negative. Nope. We'll go 0 here. 4, negative 2, and 5, negative 4. Okay. And this time I want to do some other things, like if I tell you that the initial condition here, P of 0 is negative 3, I want you to find P of 5. I want you to find the displacement from t equals 0 to t equals 5. And I want you to find the total distance traveled from t equals 0 to t equals 5. 3 pretty important calculations that we're going to be finding. All right, so probably starting with the displacement first. So displacement, oh, that was ugly. Well, I don't have a curve. How am I going to accumulate? I know I need to accumulate from 0 to 5, but I can't find the antiderivative of velocity because I don't have an equation. So how am I going to do this? We are going to use a Riemann sum. And I will always tell you what type of Riemann sum. So in this case, we're going to use a Riemann sum. I'll also get rid of this graph because we won't need it anymore. I'll use a Riemann sum. Let's use a left hand. with 5 subintervals, or 1, 2, 3, 4 subintervals, sorry. Also, I just realized that there should be one more for 0. I didn't put this at 0. Let's go to, we'll do 5 subintervals, I guess, because I'm going to start this at 0, 1, 3, 2. Okay, so, sorry, fixed it now though. So we need to do a Riemann sum. I said a left-hand Riemann sum with 5 subintervals. Sometimes it'll be a trapezoidal, sometimes it'll be a midpoint. In this case, we'll just do a left-hand Riemann sum. So not so bad. The calculation here is just left hand times the base. So 2 times 1 plus 3 times 1 plus 1 times 1 plus 0 times 1 plus -2 times 1. Because the base length is 1, the distance between each of these is 1, and we don't use -4 because this is a left-hand Riemann sum, which is 2 plus 3, so 5, 6, but -2 is 4. So in other words, according to the table, we're approximating the displacement from 0 to 5 by adding up the area under the curve using a Riemann sum, and we got a displacement of 4. Well, the next easiest question would then be, how do we find P of 5? Well, we do P of 0 plus the accumulation from 0 to 5 of our velocity, which we have our initial condition is -3 plus our accumulation, initial condition plus accumulation, which we found in the previous part. We know that we displaced ourselves 4 units. So -3 plus 4 is 1 unit. Finally, how on earth are we supposed to do total distance in this case? Well, if you go back here to the Riemann sum, so using the Riemann sum, we went a velocity of 2, a velocity of 3, a velocity of 1, 0, and then we went negative velocity. So if you come back to your Riemann sum, we can adjust our Riemann sum so that we only deal with positive values. Kind of like the same thing of taking the graph and putting absolute value on it. We're going to do the same thing. So we're going to go back to our calculation, which was 2 plus 3 plus 1 plus 0 plus, and we're going to take the absolute value of this term. Notice we're taking absolute value individually, meaning you would have actually wanted to do the absolute value term by term. And this is the only one that changes. So it's going to be 2 plus 3 plus 1 plus 0 plus 2. 4, 6, 7, 8. So that is my total distance traveled. I went from 0 to 5, absolute value of the velocity curve. And really, to do that using a Riemann sum, just change all the rectangles to positive areas. So if I'm having you find 5 rectangles and 2 of them ended up being negative, change it so that those 2 are positive and have them all be positive. All right, so these are our 3 big calculations we're going to be finding. Position at a time, displacement, which to find the position, you're going to need the displacement, and total distance, where you take the displacement, but you take the absolute value of the inside. So make sure you're taking the absolute value of the inside, not the outside. That'll mess things up. It's the absolute value of the velocity function, and then you accumulate. All right, that's it. The homework looks pretty similar to this.